Welcome back to the deep dive. Today we're doing something really specific. It's a critical mission, actually, designed just for you, the ATPL student, especially if you're focusing on that flight planning paper.
Yeah, we're diving deep, not just general aviation chat today. We're zeroing in on mastering the data extraction you need for single-engine piston performance. You know, the SE stuff.
Exactly. Using those graphs and tables you see everywhere, like in CPAP 697 materials. And our goal isn't just, a quick summary. We want to really analyze and pull out the precise, critical methods, the figures you absolutely need.
Think of it as a focused shortcut, maybe.
Yeah.
A way to confidently handle those SEP and get the exact time, fuel, distance figures for the exam questions.
Okay, before we even look at a chart, we need to be absolutely clear on the aircraft these numbers are based on. Its features really dictate how we read the data, don't they?
They absolutely do. So the reference aircraft here, it's a monoplane reciprocating engine. Pretty standard stuff there.
But the key things for the exam.
Right, two crucial features. First, it's got a constant speed propeller. That means the pilot controls pitch and RPM directly. That's important for power management.
Okay, constant speed prop. And the second?
Retractable undercarriage. And for, well, pretty much all the performance calculations will be looking at climb, cruise, descent. We assume the gear is UP, retracted.
Got it. So those features, constant speed prop, gear up. How do they link to managing the engine, particularly for theory questions? How do we adjust power?
Okay, so power is mainly controlled by the manifold pressure. You measure it in inches of mercury, NHG. More pressure, basically a denser fuel-air mix going in, so more power.
Makes sense. Higher pressure, more bang.
Pretty much. And at the same time, the pilot's managing the mixture control. You've got more fuel, which you'd use for cooling, max power, like takeoff, maybe high power climb. Or you lean out less fuel for economy cruise. And most of the cruise data we'll see assumes you've linked it properly for efficiency.
Right. Leaning is key for cruise. Now, there's a concept about climb power that often trips people up, isn't there? Something about maintaining pressure.
Yes, exactly. Let's say you set your desired manifold pressure on the ground, maybe 25 inches. As the aircraft climbs, the air gets thinner, right? The atmospheric density drops.
Naturally.
So to keep that 25 inches manifold pressure, the pilot has to physically, manually, push the throttle lever forward, bit by bit, compensating for the thinning air.
Okay, so you're gradually opening the throttle more as you climb just to maintain the same power setting indication.
Precisely. Until you can't push it any further, you hit a limit.
And that limit has a specific name.
That limit is full throttle height, FTH.
FTH. Okay, define that clearly for us.
Full throttle height is the altitude where your throttle lever is fully forward, maxed out, but the engine just can't suck in enough air to maintain that desired manifold pressure anymore.
So even with the throttle wide open,
the manifold pressure starts to drop if you climb any higher, and that means less power. And your true airspeed, your TAS, will start reducing too.
So why is really understanding FTH so critical for the ATPL student? What's the exam relevance?
It's your performance ceiling for that power setting. Simple as that. If your flight plan needs, say, 25 inches manifold pressure for cruise, but your chosen altitude is above the FTH for 25 inches.
Your plan doesn't work.
Exactly. It's invalid. You either have to accept less power and a lower TAS, or you have to plan to cruise at a lower altitude where you can maintain that pressure. It dictates your maximum effective cruise level for a given power.
Okay, that's a really crucial link. Before we hit the numbers, let's just quickly lock down the key aircraft specs from the source material, the anchor points.
Good idea. These are often given but worth repeating. Maximum takeoff mass, MTOM, and maximum landing mass, MLM, are both 300, 650 pounds for this aircraft type.
300, 650 pounds for both. Got it. Fuel.
Max fuel load is 74 U.S. gallons. And this is important, unless the exam question specifically tells you otherwise. The standard fuel density to use is 6 pounds per U.S. gallon.
6 pounds per gallon. Right. Those are the starting blocks for any plan. Hashtag part 1. The dynamics of climb performance. Time, fuel, distance.
Yeah.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best